Hello everyone, we're going to be doing section 7.5, which is on the sum and difference formulas. So we have four objectives in this section. One, we want to use sum and difference formulas to find exact values. Two, use sum and difference formulas to establish identities. Three, use sum and difference formulas involving inverse trigonometric functions. And four, we want to solve trigonometric equations linear in sine and cosine. So, all right, let's get started by defining sum and difference formulas. So sum and difference formulas are the trigonometric formulas that involve the sum or difference of two angles. So something like cosine of alpha plus beta and cosine of alpha minus beta are going to be shown below. So we have our sum and difference formulas for the cosine function first. So cosine of alpha plus beta can be turned into cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Then cosine of alpha minus beta will be cosine of alpha times cosine of beta plus sine of alpha times sine of beta. So if you have your function in this form, we can expand it out into this different way so that we can make it easier on us to actually find angle measurements of specific functions like cosine. So all right, objective one. We want to use sum and difference formulas to find exact values. So with the sum and difference formulas, we can obtain the exact value of the cosine of an angle that can be expressed as the sum or difference of angles whose sine and cosine are known exactly. So let's do our first example to kind of expand on this. So example one, we want to find the exact value of cosine of 75 degrees. So first thing we want to do is that we want to separate this into two angles that we already know. And two common angles that we already know that we can find cosine and sine of fairly easily because they're on our unit circle is going to be 30 and 45. So 75 degrees can be expressed as 45 degrees plus 30 degrees. So we can use these as well. If you wanted to, you could use a subtraction. You could use like 125 minus 50. That's not very helpful, but you could find any sort of difference as well. But if we use these angles, we know that these are pretty specific. They're just in quadrant 1 of our unit circle, so they're fairly easy to remember the values of. If you can break it down into angles in quadrant 1, which are along the lines of the most simple angles you can find in the unit circle, and you definitely want to do that instead. So all right, we can express 75 degrees as 45 plus 30. So this means that we can now express cosine of 75 degrees as cosine of 45 degrees plus 30 degrees. And now we can use our sum formula to express it as cosine of 45 degrees times cosine of 30 degrees minus sine of 45 degrees times sine of 30 degrees. Well, let's express it this way. So now we say this is equal to cosine of 45 degrees times cosine of 30 degrees minus sine of 45 degrees times sine of 30 degrees. So now that we have this expressed in this way, we're going to scoot this over a little bit so we can give ourselves a little bit more room. So now that we have this value, we can really easily find the values of cosine of 45 degrees, cosine of 30 degrees, sine of 45 degrees, and sine of 30 degrees. Just by using the unit circle, we can determine that cosine of 45 degrees is square root 2 over 2. Cosine of 30 degrees is the square root 2 over 2. Sorry, square root 3 over 2. I got stuck on that first one. Then sine of 45 degrees is the square root 2 over 2 again. And sine of 30 degrees is 1/2. So then we just want to simplify. So the square root 2 over 2 times square root 3 over 2 is going to give us the square root of 6 over 4. Then the square root of 2 over 2 times 1 over 2 is going to give us the square root of 2 over 4, which when we simplify, just simplifies down to the square root of 6 minus the square root of 2 all over 4. So that would be our answer there. Let's just kind of move this down a little bit. So we had a little bit more room for that. And this here would be our answer. So this tells us that cosine of 75 degrees gives us this value of the square root of 6 minus the square root of 2 all over 4. So we can also establish these two important identities. If we have cosine of pi over 2 minus theta, that's going to be equal to sine of theta. And if we have sine of pi over 2 minus theta, that's going to be equal to cosine of theta. We know this because of our curve shifting and our sinusoidal graphs. So we can also find the sum and difference formulas for the sine function. So now we have that the sine of alpha plus beta is going to be different. So we have sine of alpha plus beta is going to be equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Then when we have sine of alpha minus beta, this is going to be equal to sine of alpha times cosine of beta minus cosine of alpha times sine of beta. So we see that they're very similar. The only difference is related to plus or minus, which is in this case with sine, it's going to be the same. With cosine, it's the opposite. So if you have angle that is a sum, when you write out your formula, you'll have a minus sign. If you have a difference, you'll write a plus sign. For sine, it's going to be the same sign. So if you have a sum, you're still taking a sum in your formula. If you have a difference, you're taking the difference in your formula as well. So, all right, on to objective 2. We want to use the sum and difference formulas to establish identities. So example 2, we want to establish the identity that cosine of alpha minus beta divided by sine of alpha times sine of beta is equal to cotangent of alpha times cotangent of beta plus 1. So as we went over before in establishing identities, we know that one side is the goal and the other side is what we want to manipulate. So the harder side looks like this side. So we'll start with this side, and cotangent of alpha times cotangent of beta plus 1. This is going to be our goal. So first things first, we want to expand out cosine of alpha minus beta. We want to use our formula to express this differently. So when we want to express it differently, cosine of alpha minus beta can also be written as, and we can go back up and look at our formula here. So cosine of alpha minus beta is the same thing as cosine of alpha times cosine of beta plus sine of alpha times sine of beta. So let's write that out. So we have cosine of alpha times cosine of beta plus sine of alpha times sine of beta. And this is all divided by sine of alpha times sine of beta. So what we see here is that one of our terms in our numerator is the same as our denominator. Since we're adding terms in our numerator, we can also separate them out since there is one single denominator and we're taking the sum in our numerator. So this is the same thing as saying cosine of alpha times cosine of beta divided by sine of alpha times sine of beta plus sine of alpha times sine of beta divided by sine of alpha times sine of beta. So now we see that our right-hand side cancels out. And so now we're left with cosine of alpha times cosine of beta divided by sine of alpha times sine of beta plus 1. And now remember our goal is that we want cotangent of alpha times cotangent of beta. And we see we have cosines in our numerator, sines in our denominator. So we can also separate our product here out as well, so that we end up with an answer that looks like cotangent of alpha times cotangent of beta. So we can separate this into cosine of alpha divided by sine of alpha times cosine of beta divided by sine of beta. And this finally is going to give us cotangent of alpha times cotangent of beta plus 1. And these could have all been equal signs as well. So we ended up with our goal, which means we've established our identity. So all we really did in this case was we wanted to expand out our difference of angles with our sine cosine, and then simplified from there. So that was all we really did to establish that identity. Moving forward, we can also establish the sum and difference formulas for the tangent function as well. So for the tangent function, for tangent of alpha plus beta, this is going to be equal to tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha times tangent of beta. So our tangent functions are a little bit more confusing. Then we have tangent of alpha minus beta, which is going to be equal to tangent of alpha minus tangent of beta divided by 1 plus tangent of alpha times tangent of beta. So definitely a little bit more confusing than our functions of sine and cosine. But let's go ahead and establish an identity using our tangent functions. So example 3, we want to establish the identity tangent of theta plus pi over 2 is equal to negative cotangent theta. So once again, we see this is our more difficult side, so we're going to start with our left side, and our goal is our right side. All right. So what we see here is that we have tangent of theta plus pi over 2. What we see is that tangent of theta plus pi over 2 is actually not going to end up being defined. This is because we see that tangent of pi over 2 is going to be undefined, which means that tangent of theta plus pi over 2 is going to be undefined, since we would have to use tangent of pi over 2 in our actual equation. So we're actually not able to use equations 6 or 7. But what can be defined is sine of theta plus pi over 2 and cosine of theta plus pi over 2. So that's how we're going to change up our tangent of theta plus pi over 2. So this is going to become sine of theta plus pi over 2 divided by cosine of theta plus pi over 2. So this is how we end up kind of rewriting this, since we can't use equations 6 and 7. And now we can go ahead and use our sum formulas for sine and cosine. So our sum formula for cosine is going to be cosine of theta times cosine of pi over 2 minus sine of theta times sine of pi over 2. Then for sine, we can go ahead and look again. Sine of theta plus pi over 2 is going to be sine of theta times cosine of pi over 2 plus cosine of theta times sine of pi over 2. I think I might have flipped sine and cosine in the second part, but since they're being multiplied, it doesn't really matter which one you write first or second. Yeah, I did switch them. So we can switch them back, but they are multiplied. So it doesn't really matter which one you want to write first and which one you want to write second. But for clarity's sake, let's just keep these in the order that we were given. There we go. All right, so we have sine of theta times cosine of pi over 2 plus cosine of theta times sine of pi over 2 divided by cosine of theta times cosine pi over 2 minus sine of theta times sine pi over 2. All right, so now that we have these values, we obviously don't know what sine of theta or what cosine of theta is, but we do know what cosine of pi over 2 and sine of pi over 2 are. So let's go ahead and fill in those values and see if we can simplify. So sine of theta times cosine pi over 2, cosine of pi over 2 is going to end up being 0. So we have sine of theta times 0 plus cosine of theta times sine of pi over 2, which is 1. Then we divide by cosine of theta times cosine of pi over 2, which is 0, minus sine of theta times sine of pi over 2, which was 1. So what we end up getting here is 0 plus cosine of theta divided by 0 minus sine of theta. Then we get cosine of theta divided by sine of theta, and since sine of theta was negative, this becomes negative, which then ends up giving us negative cotangent of theta, which was our goal. So we've correctly established this identity since we resulted in our goal. And all we did was using this was rewriting our tangent of theta plus pi over 2. With tangent, you do have to look out for that. Anything that's going to have a vertical asymptote, you do have to look out for those specifications because you just want to make sure that those single values are going to be defined. If any one of them is undefined, then that means that the entire formula would then be undefined as well.